In this final chapter on aldehydes and ketones, we are going to examine oxygen and nitrogen nucleophiles. Specifically, we are going to look at addition of water and alcohols to carbonyl compounds, at synthesis of imines and enamines, and reductive amination. First, we are going to examine oxygen nucleophiles. Common oxygen nucleophiles are water and alcohol. Addition of water is called hydration reaction, and products are hydrates. Addition of water occurs either under basic or acidic conditions. Under basic conditions, reaction is catalyzed, of course, by the base, and aqueous base is hydroxide. Hydroxide is a nucleophile. Hydroxide ion is a nucleophile. So addition of hydroxide ion to carbonyl is the first step and results in formation of the intermediate alkoxide that is then protonated to give the final product, hydrate, and it regenerates hydroxide. From this you can see that hydroxide was the reactant and the product, which means that hydroxide is a catalyst in this reaction. Whatever hydroxide was used up in the first step is regenerated in the last step and can go back in the first step to catalyze another cycle. So base catalysis is catalytic with respect to hydroxide. Under acidic conditions, reaction is again catalytic, and under acidic conditions, first step is protonation. So carbonyl group is protonated to give oxonium ion. Protonated carbonyl group is much more reactive compared to ordinary carbonyl group and can react with weak nucleophile such as water. Water is relatively weak nucleophile. So addition of water to protonated carbonyl group results in formation of oxonium ion, and this oxonium ion is deprotonated by another molecule of water to regenerate the acid. So product is hydrate and regenerated acid. And in this case we can see that reaction is acid catalyzed. So hydronium ion, aqueous acid, is reactant in the first step, and then hydronium ion is regenerated in the final step. So reactant in the first step and product in the final step. So whatever is formed in the final step can go in the first step to catalyze another cycle. So again, reaction is catalytic. So both reactions under basic and acidic conditions are catalytic reactions, and products are hydrates. Addition of alcohols to carbonyl compounds gives a little bit more diverse compounds. So addition to aldehydes could result either in formation of hemiacetal or acetal, and ketones hemiketal or ketal. Hemi is Greek prefix for half, so hemiacetal would be half acetal. That means one substituent on the carbon is alkoxy group and the other one is hydroxy. Acetal has two alkoxy groups, and typically both alkoxy groups are identical. Of course, R group attached to carbon is usually different. And hemiketals and ketals follow the same pattern. So hemiketal, half ketal, has one alkoxy and one hydroxy substituent on the carbon, and ketal has two alkoxy substituents, and both substituents are usually identical. Base catalyzed addition of alcohols results in formation of hemiacetals. Of course, that's reaction with aldehydes. With ketones, we obtain hemiketal. So, under basic conditions, corresponding base is alkoxide. Alkoxide adds to carbonyl compound to give intermediate alkoxy compound, which then is protonated by an alcohol to give hemiacetal. And that's where reaction stops. Reaction, of course, is catalytic with respect to base. So alkoxide base is reactant in the first step and product in the final step. So it's regenerated in the course of reaction, and therefore reaction is catalytic with respect to base. So if two R groups, these two R groups are both alkyl groups, both hydrocarbons, then product is actually hemiketal. If one of the R groups, at least one of the R groups, is hydrogen, then product is hemiacetal. Under acidic, so this would be reaction under basic conditions. Under acidic conditions, reaction mechanism is a little bit longer, not much more complex, but considerably longer. And compounds that are formed are acetals. In the first step, aldehyde or a ketone is protonated, in this case aldehyde. So oxonium ion is acid in a solution of an alcohol. Protonated aldehyde, as in case of water, reaction with water, is more reactive than unprotonated species, so it reacts now with weak nucleophile such as alcohol. In the next step, the resulting oxonium ion is deprotonated by alcohol that is unprotonated, and the result is initial formation of hemiacetal. Note that this step is catalytic. So we have acid as reactant and acid as the product. So this first sequence of reactions is catalytic, but that's not the end of the reaction. So this acid could actually go into first step to catalyze formation of more of the hemiacetals. So it could simply go back to the first step to catalyze formation of more of the hemiacetal, or it can protonate oxygen of the hemiacetal, and then next compound is oxonium ion with good leaving group, with water as a leaving group. So water as a leaving group leaves assisted by electron pair from alkoxy oxygen. And next compound is oxonium ion. Oxonium ion that is derived from carbonyl compound, which means very reactive carbonyl compound. This is equivalent to protonated carbonyl compound, except that on oxygen we have alkyl group, in this case methyl group, and not proton. So it will react again with another molecule of alcohol. So second reaction with alcohol occurs, and we get another different oxonium ion, and then that oxonium ion is deprotonated to give the final product, and that's acetal. This deprotonation results in formation of acid of protonated alcohol, oxonium ion. So that acid actually regenerates the acid that was used up in this part of the sequence, in one of the previous steps. So reaction is fully catalytic with respect to acid. So both base catalyzed addition and acid catalyzed additions are fully catalytic. Base catalyzed addition gives hemiacetals, and acid catalyzed addition gives acetals. In general, we usually carry out acid catalyzed addition and we form acetals. There is very little use for hemiacetals. On the other hand, acetals are important compounds in organic synthesis and are very frequently prepared. Now we will briefly look at nomenclature of acetals and ketals. Acetals and ketals have two substituents, usually two identical substituents, and those substituents are called alkoxy substituents. Alkoxy is alkyl group attached to oxygen, so alkyl oxy or alkoxy. So methyl attached to oxygen would be methoxy, ethyl ethoxy, isopropyl isopropoxy, tertiary butyl t-butoxy, and so on. And of course, since there are two of them, we use prefix di and two numbers. They are always named as substituents. So we name molecule as you would usually name it, and then we name two alkoxy groups as substituents. Here is first example of an acetal. So longest chain here has 3 carbons, so this is propane. And on carbon 1 we have 2 ethoxy groups. So this is 1,1-diethoxy propane. Next compound is a ketal. It's again propane, but now 2 ethoxy groups are on carbon 2. So this is 2,2-diethoxy propane. Third example is another ketal, now on cyclohexane ring. You may recall that in cyclohexane, if there is only one substituent, we would not use any numbers. We would simply name substituent, and actually cyclohexane or any other cyclic compound with a substituent and a ring, like methyl cyclohexane or ethyl cyclopentane and so on. It would be wrong to use number 1. But if there are 2 or more substituents, then we have to use all the numbers, including number 1. Since there are here 2 substituents, we have to use numbers and we have to use two number ones. So it's 1,1-dimethyl cyclohexane. It would be wrong to name this 1-dimethyl cyclohexane and assume that other substituent is on carbon 1. It has to be 1,1-dimethyl cyclohexane. And the final example is a ketone, 6 carbons and keto group on carbon 2, so this is 2-hexanon. On carbon 5, there are 2 methoxy groups, so this is 5,5-dimethoxy 2-hexanon. Acetals and ketals are mainly used in organic chemistry as protective groups. And as protective groups, usually we use cyclic acetals and ketals. The reason why we use cyclic acetals and ketals is that they are more stable compared to open chain acetals and ketals. And you can see it from this example. Acetals and ketals are readily hydrolyzed. They readily lose one of the alkoxy groups, and once one group is gone, the other one is very quickly removed. So very easily one carbon-oxygen bond is broken, particularly under mild acidic conditions. Even very small amount of dilute acid will cause hydrolysis to corresponding carbonyl compound. So one of the carbon-oxygen bonds is broken, assisted by the electron pair from the neighboring oxygen, as you can see here. If acetal or ketal, in this case, is cyclic, then even though carbon-oxygen bond is broken, that oxygen that just left is now nucleophilic oxygen and is still attached to the other oxygen chain, is still attached to the rest of the molecule. So that oxygen is in the vicinity of the carbon, and that carbon, the other end of the double bond, is now electrophilic carbon. So the bond is most likely to be reformed and ketal would be reformed. So it would remain intact. On the other hand, if you are dealing with an open chain compound, once one of the alkoxy groups is gone, it's pretty much gone forever because it leaves vicinity of the molecule, or what is now an oxonium ion, and it's not possible for it to react back with it. And oxonium ions are highly reactive, and so they are likely to be hydrolyzed further to the corresponding carbonyl compound. And here are some examples of use of ketals. Acetals also could be used, but these examples all involve ketals, of use of ketals as protecting groups. This first example involves Wieland-Mischler ketone. That's a ketone that was developed in the synthesis of steroids. So it has 2 fused cyclohexane rings and 2 rings that we can identify as A and B rings. A ring has double bond conjugated to a carbonyl group, and B ring just has a carbonyl group. Conjugated carbonyl group is a little bit less reactive, at least at the carbonyl carbon. So B ring has carbonyl group that is more reactive. But let's say we want to react carbonyl group of A ring, less reactive carbonyl group, in a Wittig reaction to form a double bond, as shown here. So how we would do that? Direct reaction, if we use only one equivalent of Wittig reagent, would occur on ring B, and we would not get desired product. So what we need to do is first react more reactive group. So we treat this compound with ethylene glycol. So this is diol. It's an alcohol 1,2-ethane diol, or trivial name ethylene glycol, in the presence of an acid catalyst and under anhydrous conditions, and that produces cyclic ketal. Now again, more reactive carbonyl group reacts, and while in our previous analysis we didn't want more reactive keto group on ring B to react, now more reactive one will react on ring B to form ketal, while one on the ring A will remain intact. Next, when we react protected compounds with a Wittig reagent, now we have only one carbonyl group. The other group is protected as a ketal. And so reaction with Wittig reagent reacts only with remaining carbonyl group to give the corresponding alkene. And in the final step, we remove the protecting group. So that's shown here. So in the final step, we remove the protecting group with dilute acid and obtain desired compound, desired diene to alkenes and ketones, so desired diene ketone. Another example is reaction of this chloroketone. We would like to extend the chain by one carbon atom and prepare hydroxyketone. So how are we going to do that? The best way would be to convert carbon-chlorine bond into organomagnesium or organolithium bond and react that with formaldehyde. That would extend carbon chain by one atom and form the corresponding alcohol. Problem is that these compounds, Grignard reagents or alkyl lithiums, react with carbonyl compounds. And since in this case you would have both organomagnesium or organolithium compound and carbonyl group in the same molecule, they would be very close to each other and would very quickly react with each other to form a ring. To avoid that, then we protect first carbonyl group as a ketal. Here we are using different diol, 1,3, a propane diol. This one forms 6-membered ketal. So just to be different, just to show you two commonly used cyclic ketals. Again, acidic catalyst and anhydrous conditions. And now that we have protected ketal, we can react resulting chloroketal with magnesium in ether. That would produce Grignard reagent, and then that Grignard reagent will react with formaldehyde to give corresponding alkoxide with one additional carbon atom. And then acid workup will actually accomplish two things. It will protonate alkoxide to alcohol and will also remove ketal protecting group to give desired product. It would give desired hydroxyketone with one more carbon atom. So these are two examples of use of acetals and ketals as protecting groups. Protecting groups are commonly used in organic synthesis and have a very important role because they protect groups that would otherwise react from reacting and allow us to carry out reactions elsewhere in the molecule. A drawback of use of protecting groups is that two additional steps are added to the sequence. One step to introduce the protecting group and one step to remove it. And that of course means added time, added expense, and sometimes reduced yield. But still, that's better than not being able to do this transformation at all. And finally, we're going to have a look at nitrogen nucleophiles. Those are amines, hydroxylamine, and hydrazines. Ammonia and amines readily react with carbonyl compounds. Primary amines react with carbonyl group to give so-called Schiff bases. A Schiff base has carbon-nitrogen double bond and an alkyl group attached to the nitrogen atom. Secondary amines, of course, cannot form carbon-nitrogen double bonds since they already have two alkyl groups. So secondary amines react with carbonyl compounds to give so-called enamines. And enamine means alkene, that's in, alkene amine. So they have amino group attached to carbon-carbon double bond. Hydroxylamine readily reacts also with carbonyl compounds to give corresponding oxime. And oxime is a compound that has carbon-nitrogen double bond, and now substituent on the nitrogen is hydroxyl group. Oximes were very important in the past because oximes are very easily produced simply by mixing hydroxylamine and carbonyl compound. Oxime will be generated, and oximes have often low solubility, so they precipitate. They often precipitate as nice clean powder. So they were used first to purify carbonyl compounds because compound could be precipitated as an oxime. Then those oximes could be filtered and if necessary further purified such as recrystallized. And then they could be hydrolyzed back to carbonyl compound. Just now carbonyl compound upon hydrolysis is pure. Also oximes have very sharp melting points. And so in the past, before advent of spectroscopy, they were often used to identify carbonyl compounds. So there were long tables with lots of carbonyl compounds and their oximes and lists of melting points, and so you take melting point and then match it with melting point from the table to identify carbonyl compound. These days we use spectroscopy for that. And finally, another important compound are hydrazines. So hydrazine itself is shown in the reaction on the left. So two amino groups attached to each other, that's hydrazine. And hydrazine reacts with carbonyl compounds to give corresponding hydrazone. Hydrazones, just like oximes, are white crystalline solids and, like oximes, could be used for purification or identification of carbonyl compounds. If we react them in 1:1 ratio, this is what we get. We get hydrazones. We can also react them with two equivalents of carbonyl compound where both nitrogen atoms react, but that's less common. Besides hydrazones, we even more commonly were using derivatives, particularly phenyl derivatives of hydrazine. So either phenylhydrazine itself, or this is another commonly used derivative shown here in the reaction on the right, 2,4-dinitrophenylhydrazine. And so compounds products are 2,4-dinitrophenylhydrazones. Again, those were brightly colored compounds. Sometimes from the color we could get information whether it's aldehyde or ketone. And again, they were used for purification because they were nice crystalline compounds. It could be recrystallized and further purified, and also had sharp melting points. Hydrazine and derivatives of hydrazine are almost never used these days, and the reason for it is their high toxicity. They are extremely toxic, both acute toxicity, which means they will immediately harm a person, and also long-term toxicity. Long-term exposure results in cancer and other toxic effects. And they are readily absorbed to skin, so these days we almost never use them. Simply they are just too toxic for ordinary use. Now we are going to examine mechanism of formation of imines. So a reaction starts by donation of free electron pair from nitrogen to carbonyl carbon. That forms nitrogen-carbon bond, and that's very facile reaction because nitrogen is an excellent electron pair donor. It's very strong nucleophile. So this step occurs very easily, and resulting product intermediate is shown highlighted in yellow on the right. Actually, it is a Zwitter ion. It contains alkoxide anion and ammonium cation in the same molecule. Next step is transfer of proton from nitrogen to oxygen. But that step cannot occur intramolecularly. It cannot occur intramolecularly because geometry is not correct. Orbitals are not aligned properly. And that's shown here at the bottom. Electron pair from oxygen would have to be donated to the antibonding NH orbital, nitrogen-hydrogen orbital, but it has to come from the back. It has to be backside attack. And obviously that is not possible given where the oxygen atom is. So for that reason, something else has to donate proton to oxygen and remove proton from nitrogen. So these next two steps can occur in any order. Either first proton is donated to oxygen or removed from the nitrogen. So here we have a first donation of proton to oxygen. So it picks up proton from hydronium ion, and we end up with alcohol group and ammonium cation. In the next step, a molecule of water picks up a proton from nitrogen, or any base picks a proton from nitrogen, and now we end up with alcohol amine as an intermediate. So that's shown here. In the following step, alcohol is protonated to oxonium ion, and as such it's a good leaving group. So it leaves assisted by the electron pair from nitrogen. When that happens, we end up with another ammonium cation, and finally removal of proton from that ammonium cation results in formation of an imine. So as you can see, mechanism is rather long, a lot of protonation, deprotonation steps, and addition, elimination steps, but it's not very complex, it's just that it's long mechanism. And of course, all of the steps are reversible, which means that starting with imine and water, this reaction would work back to carbonyl compound. And in fact, carbonyl compound is more stable than an imine, which means that in presence of water, imines are readily hydrolyzed back to carbonyl compounds. Reaction of secondary amines with carbonyl compounds results in formation of enamines. And here are several examples. For example, reaction of cyclopentanone with diethylamine results in formation of this corresponding imine. And some more examples. Frequently cyclic compounds are involved. So either carbonyl compound could be cyclic, or secondary amine could be cyclic, or both of them could be cyclic. And this last example involves one very commonly used secondary amine, and that's morpholine. So this 6-membered ring that contains oxygen and nitrogen atoms in para position is called morpholine, and it's very commonly used secondary amine to prepare enamines. Enamines have extensive use in organic synthesis. They are used in alkylation of carbonyl compounds, and that will be covered in chapter 23. Enamines are very easily hydrolyzed. In fact, their hydrolysis is even easier than that of imines. So for that reason, enamines have to be carefully protected from even traces of moisture. They will hydrolyze even if they are exposed to atmospheric moisture, just to wet air, which is always present. Some moisture is always present in ordinary air. So they have actually either be prepared immediately before use, or if they are going to be stored for any period of time, they have to be completely protected from exposure to air and moisture. Otherwise, hydrolysis will occur and will obtain a carbonyl compound back. And here is the mechanism of formation of enamines. And you can see it is identical to that of imines, except for the very last step. So when we consider the mechanism, first step, as usual, is addition of nitrogen nucleophile to carbonyl carbon. That results in formation of a Zwitter ion, which is then protonated. It's protonated on the oxygen to give this next intermediate, which is ammonium alcohol. This is the intermediate that could also be obtained in a slightly different way. So first step could actually involve protonation of the carbonyl group followed by attack of the nitrogen nucleophile. And actually this step could also operate in synthesis of imines. So either way, through either of the two possible pathways, this ammonium alcohol could be obtained. Then in the following step, ammonium alcohol loses a proton, and we have amino alcohol as the next intermediate. Amino alcohol is protonated on the oxygen to generate a good leaving group, oxonium ion. That oxonium ion leaves as molecule of water, assisted by the electron pair from the nitrogen. The resulting product is what is called iminium cation, and this iminium cation in synthesis of imines would lose a proton to give imine. But this nitrogen does not have a proton attached to it, so there is no proton from the nitrogen to be removed. For that reason, proton is removed from the neighboring carbon. So from the neighboring carbon, one of the available protons is removed. That results in formation of carbon-carbon pi bond, and electron pair from carbon-nitrogen pi bond flows to nitrogen and ends up being as free electron pair on the nitrogen. And so that's the resulting molecule of an enamine. So as you can see, the only difference is the very last step, difference between formation of imine and enamine, the very last step where the proton is removed from. In case of imine, there is proton on nitrogen, so it could be removed, and that's the one that is removed. In formation of enamine, since there are no protons on nitrogen, proton has to be removed from the neighboring carbon. And finally, we should look at reductive amination. Reductive amination is a sequence of two steps that is used to produce amines, to synthesize amines. Selective synthesis of primary, secondary, or tertiary amines is always a challenge. SN2 reactions using either ammonia or smaller amines, less substitute amines, and alkyl halides often suffers from excessive reaction, excessive alkylation. So it's very difficult to stop reaction, let's say at primary amine. We end up getting secondary, tertiary amines and quaternary ammonium salts and mixtures of products. So for that reason, it's always a challenge to make selectively primary, secondary, or tertiary amines. And one way to do it is reductive amination. So that sequence of two steps, first amination, and then reduction. To prepare primary amines, we react carbonyl compound with ammonia. Resulting intermediate imine is reduced, and there are two possible reducing agents. We can either carry out catalytic hydrogenation. For that we use hydrogen in presence of nickel as a catalyst, or we can use sodium cyanoborohydride. I will mention more about that when we cover next reaction. So in this case, let's say this imine, there are two, as I said, there are two possible reagents, so we chose to use catalytic hydrogenation reagent. And so catalytic hydrogenation, hydrogen is double bond to a single bond as to hydrogens across double bond, and product is amine, primary amine. So reductive amination of a carbonyl compound with ammonia results in formation of primary amine. If we carry out reductive elimination of carbonyl compound with primary amine, product is secondary amine. So in this case, reductive amination of benzaldehyde with methylamine results in formation of an imine. And now we use sodium cyanoborohydride. We could have carried out catalytic hydrogenation as in the previous case. But now we used sodium cyanoborohydride to produce or to generate secondary amine. Sodium cyanoborohydride is used as reducing agent because it has low reactivity. It is not reactive enough, like sodium borohydride, that it would reduce carbonyl compound. If we used sodium borohydride here, it would have reduced carbonyl compound, original carbonyl compound benzaldehyde to benzyl alcohol, and then reaction would not proceed because benzyl alcohol does not react with methylamine. So for that reason we have developed a reducing agent that is less reactive than sodium borohydride. Recall when we covered sodium borohydride reductions after the first step, when methoxy ion ends up attached to boron, when we end up with methoxyborohydride anion, that's less reactive than borohydride anion itself because of the electron withdrawing substituent. So we have prepared reagent like that to use it in reductive amination. Just instead of methoxy, we use cyano substituent. So cyanoborohydride is just reactive enough to reduce imine, but not reactive enough to reduce carbonyl compound. So it has very high chemoselectivity. It's very good at distinguishing between different functional groups and only reduces those that are very reactive, but leaves those less reactive intact. And so sodium cyanoborohydride in presence of methanol as a solvent results in formation of secondary amine. And finally, reaction of a carbonyl compound with a secondary amine again results in formation of, in this case, iminium cation, and then sodium cyanoborohydride reduction results in formation of tertiary amine. So this is good method. Reductive amination is a good method to prepare primary, secondary, or tertiary amines. Primary amines are prepared in reductive amination of carbonyl compound and ammonia, secondary amines, carbonyl compound and primary amine, and tertiary amines, primary compound and secondary amine. And this completes our chapter on aldehydes and ketones. Next, we are going to start chapter 22, which covers carboxylic acids and derivatives.